All right. Let us have a little look here. Let's go back in time. Talk to let's go back to chapter. This is a year ago here. I want to press upon you. We're doing here in chapter. What's coming up? I'm just picking a couple of random slides here. Here we go. Here. This is an example of what you're going to need in terms of derivatives, okay? Because we're doing mostly antiderivatives in this class, but you have no prayer of doing that unless you know derivatives, okay? And so this is one example from chapter 8, and this is by no means a hard example, okay, from chapter 8. But don't worry about this process that's being taught here. It's called partial fractions. I'll do partial fractions here. I'll show you. But what I want you to see is you have 3 different components here of this integral. Once you do this partial fractions process, you have 3 different components, right? You have, why is that? You have component number. This integral breaks down to this. Don't worry about how we do that. But you, right now, coming into Calc 2, have enough calculus, or should have enough calculus, to integrate that, that, and that. All 3 independently. This integrates to a natural log, right? Actually, no, check that. This breaks up into 2 integrals. One integrates to a natural log, one integrates to an arctan. Do you know arctan antiderivatives? That's chapter 5 in the book. We did it. I know she and I did it, and I'm not saying it's you got to have them ice cold right now because you studied them a couple months ago or whatever, whenever you studied them. But I'm telling you, if you don't know the derivative of arctan, you're not going to get its antiderivative. If you don't know how to take the derivative of something like this, you're never going to get the answer. Right here, this breaks up into 2. Look at that. This goes to this one. That goes to a natural log. And then this one just integrates into a straight up, it's a power rule thing. So in one integral, you got something that integrates to natural log, to an inverse trig function, another natural log, and then this is just a power rule. Right. I can't impress upon you enough. You're going to have to know how to take derivatives ice cold, because you're going to have to learn how to work something into a derivative to take its antiderivative. That is absolutely positively essential. So that's the purpose of these 2 quizzes I did. Right? That's the purpose of the 2 quizzes I did. And one way or another, here, let me ask on here. One way or another, we got to get this up a little bit here. So now here's what I'm going to do. Here's what we're going to do. Okay. I want you to take a look at there. In each case, I gave you the formulas to start. I gave some indication of where you went off base. I did not correct your work. I did not correct your work. I want you to correct your work. Now, here's what I want to do. Okay. I want you to look at your papers, look at the problem. You know the problems. You know the type problems. There's a product rule and a quotient rule. And then I want you to stop by my office in one of those times, come by my office and make corrections on that to earn some points back. Okay. In fact, you know what? You know what? Because I'm a swell guy, I am going to. I want you to correct those, and I will grade them again as if you'd never taken it. Okay. So each of you have an opportunity to make 5 out of 5 on that. So only worth 5 points, not worth a ton. Should be worth more because it's 5 points underestimates its importance. It underestimates its importance. So it's only worth 5 points, but you both have an opportunity to make 5 out of 5. But you absolutely have to learn the product rule in the course. You just have to. Oh, for that matter, the chain rule. The chain rule is buried in there too. Okay. There's I could keep going through the I could keep going through the slides here. Let's see what we have next here. Let's go back up here. Let's go back. I'm just showing you notice here, every one of these problems, we're going to be doing this. This is my Cal 2 slides from last spring. Right here, trig substitution. And you're working things into the derivative of other things. Now, don't worry about the technique here. That you shouldn't be expected to know right now. What you should be expected to know is derivatives. So you've got to work this into something like, for example, that works down to this, right? Cancel out some stuff, and that's the integral of cosecant. The integral of cosecant, the antiderivative, is something you either need to know or know how to get. You either need to memorize it or remember how to get it. Now, at this point, I've done it enough times in this class that I just wrote it out what it is, right? But you see what these answers look like, right? That's the rest of the problem, okay? This is only the halfway point in the problem right here. It goes on to another screen. And so this is the kind of stuff you're going to be doing. You can't be stumbling over derivatives. And the absolute key to doing well in calculus, as my D in Calculus 2 testifies, right, is an ice-cold mastery of derivatives, right? And when I took Calc 1, I finally had to study, but everything was a couple nights before. And honestly, if I told you the story, my girlfriend wasn't in there. It wouldn't have happened if it was left up to me, because I know me. So your mission, this week now we have 2 quizzes, because the second quiz is on chapter 5, derivatives. So we're gonna throw in basically transcendental functions, right? Transcendental functions, trigonometric functions, log functions, exponential functions, right? So the quiz this Friday will be on those functions, right? It'll be similar to this. It won't be long, and honestly, in my modest appraisal, I think this quiz was fair. So I'm going to take these quizzes back up. Okay, take a look at them good. I'm going to take them back up, and you come by my office sometime this week between now and Friday. Now, don't do it on Friday, or you'll have 2 quizzes on Friday to do. All right, but if you can, if you want to. So I'm giving you enough rope to hang yourself on Friday if you want to. Right? I don't want you to hang yourself. Come by my office. We can work problems like this. I'll write a problem on the board. I'll do it. I'll erase the problem. And I'm going to write another problem and hand you the chalk. That's how it's going to work. I want you to have hands on these things. And it's like the weight room. It's reps. Right? Reps. And there's no this just isn't a shortcut. So this week, reps on the product rule, quotient rule, chain rule. Right? Product rule, and I guess power rule. The power rule is where you take a power down, subtract 1 from the exponent. You have to do that too. So all four of those were in those two problems. One was primarily power rule problem, and I gave you the power rule if you missed it. I wrote it out. But you have access to that. You should know it. And the other one was a quotient rule problem, primarily. There's other ways of doing both those problems, but that's the most straightforward way. So help me help you. Come in. I'll do a problem, and then I'll put you on the squat rack. You know. Right. It isn't fun. And I've walked a mile on these moccasins. I walked a mile. I told you the whole story. So anyway, okay, let me grab these, and then come by my office. I'm gonna pretend like I never graded. All right. Different color area, right? I'll pretend like they're totally blended. Or I just might turn off two other ones to keep your blankets. How about that? Something like that, okay? Same problems. You have a chance to make 5 and 5 on this. Okay? My biggest thing is I want to somehow incent you to learn and to get back and review the product rule and quotient rule. It is just absolutely essential. There's no substitute. There's no tricks. There's no coping mechanism that can learn. And I'm testimony myself of that. All right, moving on. All right, here. No, not chapter 7. Not chapter 7, chapter 6. Look at that. I said, I don't think we're that far along. It's going to be long slides. I agree. Okay, here's what we're doing. It's a lot cooling. Oh, right. We're in the middle of a homogeneous differential equation. Right, here we go. And we were in the middle. And this homogeneous differential equation we were doing by change of variables. And so we had a theorem that said, let's back up, theorem 6.2, that said, if I have a differential equation in this format here, or that can be put into that format, it probably is not going to come to you in that format. You're going to have to recognize that it can be put in that format. By the way, everything I said about the reps, it's that squared when it comes to differential equations. Your biggest obstacle is going to be able to recognize what kind of differential equation each one is. Because now that we're in the section on this particular technique, you know what every differential equation is going to be. It's going to be this technique. But when you have them scrambled up on a test or different order, which you will find them that way in the review questions for chapter 6. That's why you should allow time to review. Okay, so when this is a homogeneous differential equation, when is it homogeneous? When each of these m and n are both homogeneous functions of the same degree. They're both homogeneous of degree 2, both homogeneous of degree 3, what have you. If that's the case, then substituting in y equals vx will turn it into a separable differential equation. A separable differential equation, instead of an x and y, it turns into a separable differential equation in x and v. So here first, here's our differential equation. We had to check if it was homogeneous. There wouldn't be much point to this problem if it wasn't, but you should know how to do this. And I want to see your verification of this, okay? 2. Since it is homogeneous, I'm going to plug into my function for y and y prime. I'm going to eliminate y. And I'm going to use y equals vx. Everywhere there's a y right here, y vx. There's a y squared there, vx squared there. Okay. Then I have a y prime, And for the y prime, this is the derivative of that. You got to remember that both v and x are both functions of x. So the derivative of y equals vx isn't just v. It's first product rule. First times the derivative of the second gives you v, plus the second times the derivative of the first gives you x. That's the second. Derivative of the first is dv dx. All right? And so that gets plugged in right here. Then you have a boatload of algebra. What is your goal? Because now that you've plugged this in, our theorem says that is a separable differential equation in x and v. That's what that says. Did I mention you got to do a bunch of these buzzwords? Yeah. All right. And so what I'm trying to do here in this algebra is separate them. I want x is on one side with dx. I want everything with v in it on the other side with dv. And I eventually got that. Here's all the x's with dx. And then there is the v's with dv. I'm going to integrate both sides. Okay, let's go here. My second. No, I'm going to keep doing it on this page, and then I'm going to put it on the second page. Okay? So now I have integral on one side, integral on the other side. This side is v 4 plus v squared dv equals. There's a 2 in the bottom. I'm going to put a 1/2 out here. And I cancel the x squared, so I have 1 over x dx. Pop quiz. Pop quiz. This is why you need those derivatives. What is the antiderivative of each of these? What are each of those indefinite integrals? The antiderivative of 1 over x and the antiderivative of v over 4 plus v squared. I want you to write out on your paper what you think the antiderivative of each of these sides are. I'll give you a clue. They're similar, actually. They're each the same kind of integral, of antiderivative. I'll give you another clue. We've done several. We've done several. We've done several. One common antiderivative of fractions like this is logarithms. Isn't always. It's not always. But a common one is logarithms. Especially when the bottom has its derivative up top. So when the top is the derivative of the bottom, that goes to a natural log as an antiderivative. So over here, this becomes 1/2. That is, told you before, right? I'm going to erase this. D du of log u is u prime divided by u. That's where you have to know the derivatives. You got to. And so if you know that what the derivative of this is, you'll know that the integral of this, or the indefinite integral of that, is, and you actually have to put an absolute value sign around it, plus c. this becomes then log absolute value of x plus a constant. This cannot be a challenge in this class because you're already learning differential equations. If you're learning your derivatives at the same time and you're not sure of them, no chance, no chance. That's a soccer team forgetting its cleats, right? Won't work. Now this one, I told you they're the same type, right? So for this one, I want to make the top the derivative of the bottom. What's the derivative of the bottom? 2v. So I'm going to put a 2 up top. That makes it the derivative of the bottom. And I put a 1/2 out here to compensate.
Can you do it separate, like to see the difference?
This separate?
Yes.
So in other words, integral of v over 4 plus v over v squared. That's what you mean?
Not like. So in other words, it's gonna be 1/2 2b.
Oh. Yeah, I see what you're saying. Separate top and bottom.
Yeah.
Oh no. No, that's a very big mistake. And the reason why, very simple. The integral of f over g does not equal the integral of f divided by the integral of g. Also, as you saw in this quiz, the derivative of fg does not equal f prime g prime. Also, as you saw in this quiz, the derivative of f over g does not equal f prime over g prime. None of those work. This you need the quotient rule, that you need the product rule. And those are what I wrote in your papers. Now, you'll know you're ready to correct that quiz when you do these kinds of derivatives and get several of them right in a row. We'll say it again. You know you're ready to do those two derivatives when you've done several of them similar in a row and got them correct. If you really have never got one, or maybe you struggled and got one correct and you're missing the next one, you're still not fluent. You're not ready for. If it were baseball, it would be like, again, you played first and third?
Yes, sir.
It would be like line drive to third, men on first and second, or say second and third. Line drive to third, you know a third baseman doesn't think twice where that ball needs to go. You know exactly where that ball needs to go. Probably home, I guess, if it's on second and third, right? Something like that. You know exactly. And it's almost like, you get the ball third. What was that? And it don't work that way, right? It don't work that way. And it's the same, it's going to be the same. Now, you're not going to be graded on speed. You're not going to be graded on speed. But you will be, it's almost like if you were in baseball and you got hit to third and they were out if you threw it to the right place. Right? You can't think about it a long time, but if you say, hey, you know what? I got it. It goes home. Line drive to me, or bouncer to me, grounder to me, that goes home. I know that. Or wherever it goes in third. I don't even know. Obviously, I don't know baseball. My point is, you got to get it right. You're not going to be graded on speed. You're going to be graded on action. Now, with fluency comes speed. Right? With fluency comes speed. All right. So here, This is going to be 1/2 natural log squared, and then plus c, which we're going to put all that over here in C1. We're going to combine the c's into a place.
What happens if you don't bring the 1/2 to the front? Like, let's say you forget that step and then.
You're going to get in trouble. You'll get in trouble in this step. So if you don't have that 1/2, up here you need the 1/2 because you got to you're multiplying by 1, right? And never underestimate the power of multiplying by 1 or adding 0 strategically. So the 2 and the 1/2 cancel. So you basically multiply by 1. So if you leave this one off, you're going to have this one left off here. And now in this step here, you're going to have a problem, right? Because right now these cancel. Now you can still work through the problem, but it's going to be wrong for the rest of the way. But like right now, if you didn't have this 1/2 here, you wouldn't be able to do what I'm about to do. Cancel. And what you would have, say you had the 1/2 over here and you forgot the 1/2 here, here's what you'd have. Right now, we're going to exponentiate again, right? E to each side. Right? So we're going to do E to that side, E to this side. And we've done this a bunch of times. Now, if you still had a 1/2 right here, that 1/2 would have to go up the top and make it a square root of
On
x.
the left side, we don't put a plus c.
Well, like I said, there is a plus c here. Say right there. But you combine those two, and that makes this constant here. So you, if you're getting a constant on each side, I wrote it that way for a long time. Just combine them, make it one constant. And you can put that on either side. So here, this side now becomes what? E to the C1 times e to the natural log of x. And e to the C1 becomes C2. E to the log x becomes absolute value of x. Over here, you just have
4 plus b squared.
Now, what do we do? What are we solving for here? When you're solving a differential equation that's in x and y, we're solving for y if we can. Well, I don't even have a y left there, right? I don't even have a y. Where's my y? Right? My y is over here. Over here. Pull all this here. Right here, there's my y. That's a key relationship. Anytime you do a substitution, sometime later in that problem, you're going to have to unsubstitute. We introduced this v out of thin air, right? At some point, we're going to have to get rid of the v. So what happens? Let me see something here. Yeah, let's do, I'm going to rearrange something. This is not essential, but it's just a preference. Now, over here, I want to get rid of the v.
How do you get rid of both exponential?
Well, e to the log of anything,
Yeah, on the side.
and then here, e x to the a plus b equals x to the a times x to the b. So E to that sum equals E to the first thing times E to the second thing. I just put the C1 up, this one up front. Basic property of exponents. Now this part here, I'm even going to play with. This is important. This is a different step. What do we have to get rid of over here? The V, not the X. The X can be part of my answer, but the V, like this original problem, it knows nothing about V, right? You mentioned V to it, it goes, what? So we can't have V in our answer. We used V as a tool here, and now we got to substitute back. So this here implies V is Y over X. So down here, we're going to have did I mention these can be long? Yeah. But, oh, these aren't the longest. And so from there, we get what? Multiply through by x squared. This right here equals what? That equals y squared divided by x squared, right? Multiply through by x squared, clear the denominators, you get y squared is C2, absolute value of x cubed minus 4x squared. And there, here's your answer. You can take the square root of both sides or not. If you took the square root of both sides, you'd have to put plus or minus. You can leave it like that. Actually, a little more correct, I would say just to get rid of that 2 altogether, just put a constant there. So, yeah. So a problem like this, it incorporates so many of the fundamentals. Right? So many of the fundamentals. Let me get back down here. That's probably where you need, right? And so if somebody is weak in the fundamentals, and that was my problem with Calc 1. I crammed everything the night before in Calc 1. And I wouldn't even have done a good job of cramming as I did if my girlfriend wasn't there. I got Calc 2, and there's too much I'd forgotten in 2 months. Right. Yeah. So, oh, by the way, like a fool, once I got a D in Calc 2, I went ahead and took Calc 3 anyway. Not a good idea. I did better in Calc 3 though, because I got my head handed to me in Calc 2. I had to go back and take Calc 2 like later on when I had room in my schedule. Yeah. So let's go over the major steps again. Step number 1's over here. You've got to recognize that as a homogeneous equation, that differential equation. There's going to be other kinds of differential equations we're going to be doing. So you might try to fit it in this form or the other form, right? There's going to be different forms of differential equations. We're not going to do too many, but we do have a couple more. Right? So you suspect this is homogeneous. You put it in this form. This is a key form. This is a key step here. This step right here is key. Why is that key? Because that is your standard form. That tells you what M and N is. That step there tells you what the M is and the N is. And you got to check each one of them by plugging in Tx and Ty. You find out each of them are homogeneous at degree 2. They're homogeneous, both, and they're both homogeneous at the same degree. So it's homogeneous. That means I can apply my theorem. I can apply theorem 6.2. Theorem 6.2, you whip out y equals Vx. Anytime you do that, you might as well take its derivative because you're going to need this. It ain't a differential equation if you don't need the derivative. Because you remember, definition of a differential equation is an independent variable x, a dependent variable y that depends on x, and one or more of y derivatives. So you need this in one of the derivatives. You plug those in, and you have an ocean of algebra. But remember what your goal is. Your next main step is right here. Your next main step is right here. I'm going to right here. That is your next key step. Right? Because you're separated, right? And that is what the theorem guaranteed you. The theorem guaranteed you that if it was homogeneous, substituting y equals vx would make it a separable differential equation, which we know how to solve, right? Okay. So here, it's separated. We know how to solve those, and we did. But even the solving there, is a good bit. Right? Any questions on that? Now, what I'd highly recommend right now, this afternoon, not 10 o'clock or 11 o'clock tonight, this afternoon, I would write out that problem, the same problem, on a fresh sheet of paper and try to do it from scratch. You got the answer right there, right? Force yourself through those things on your own. It's almost like, you've been shown three different times how to go to grandma's house. Well, it's time to practice going to grandma's house, right? Do a familiar one. That way you'll learn the basic steps of the process. And I highlighted those in the bold, okay? All right, let me put this on a separate page. Sheet here. Okay. Oh, Head Trip Monday. No, whoa. That's what your brain's like Monday after a long holiday. Am I right? Am I right? It's a little bit right. By the way, I fully endorse the sleeping, by the way. Fully endorse it. I try to get a few extra seasons on the weekend myself. That rejuvenates your prefrontal cortex. And that's where you do math. It's in the prefrontal cortex. Okay. What we got here? Now, is this going to be homogeneous? Yes, it will be homogeneous. Okay, because we're in the homogeneous section, right? Okay, but verify that it's homogeneous, right? I want to see the work for its homogeneous. I'm going to look for that on the test. There will be no full credit answer without checking the assumptions of the procedure you're going to use, right? And like right here, here's a case where I took the square root and did plus or minus. But I don't care if you take the square root, make that a y squared there. I'm cool with that, right? Right? Kind of a strange looking answer. No, a little bit different looking answer. So that's going to be separate. That's going to be homogeneous. You plug in y equals vx. Plug in what the derivative y dy dx is. Right? You plug that in. That's going to make it a separable differential equation in x and v. You're going to separate it with a bunch of third grade algebra. Integrate both sides, and you're going to know how to integrate, right? Okay. And then you might wind up with logarithms. What happens if you get a log on one side and not on the other? How about if you have here, and you don't have a log right there? So suppose you work down and you just had that on that side, not the log. How would you proceed? Well, you don't really care. V, as long as you can get your hands on V, you're good. You want V outside of any log or whatever, okay? So if you were like down to here, right, you wouldn't need to exponentiate. Right? You would still have to plug in this V. This V equals y over x, put it right there. Right? Now, how about over here? How about if this were a log? Right? Then you probably do need to, you are going to have to exponentiate. If this were not a log here, you still need to get the v out of the log there. So you'd exponentiate both sides, and you would have an e to the absolute value of x. That log's gone, right? So you'd have e to the absolute value of x, and that doesn't simplify. E to the absolute value of x is e to the absolute value of x. Okay. So you would have an e to the absolute value of x in your answer somewhere. Okay, moving on. Logistic growth model. Now, I mentioned this before. Remember we were talking about uninhibited exponential growth? A population will grow in an uninhibited manner as long as there's not scarcity of the resources. So the rabbits in my backyard, right? If there was unlimited resources, and there's always unlimited resources, no matter how many rabbits there are, there's 2 rabbits or 4,002, and all of them still had the best hiding places, all of them still had the best food, etc. Then it would keep growing exponentially. It's the scarcity of resources that slows the growth rate. The scarcity of resources that slows the growth rate. And so when resources get a little bit more scarce with every individual that comes into the population, right? Not noticeably, you had one more rabbit out back, right? But everyone is going to put a little more strain on resources. Right? Sort of like everything you take in your car reduces gas mileage a little bit. You take an extra ink pen in your car, it's a little more weight, right? Not much, But how about if you take 4 cases of ink pens that weigh 200 pounds? That's a whole extra person, right? So that's going to slow your gas mileage. How about if you take 2,000 cases? That slows your gas mileage. You see what I'm saying? It's a little thing. So every individual in the population is going to slow the growth rate. Now, there's an assumption here in the exponential model. Or excuse me, in the logistic model. Okay. There's an assumption. What's the assumption? Well, there's a bunch of them. But one of them is every individual decreases the growth rate by the same amount. So you got 2 rabbits. The 3rd rabbit decreases the growth rate by the same amount, or by some amount. You have 4,002 rabbits. The 4,003rd rabbit will decrease the growth rate by the same amount as the 3rd rabbit did. That's an assumption. May not be true in real life. And believe me, they have more sophisticated models of this that allow for the growth rate to decline at different amounts for different amounts of rabbits. Right? We're not going into that. Now, what this means, and I mentioned this before, what this means, and this seems like a reasonable real life assumption, is that if my backyard is a closed ecosystem, no rabbits go in or out, right? No predators go in or out. If that were the whole universe, there's a maximum number of rabbits that can live back there. I don't know what it is. It may be 4,002. It might be 4,000,002. I don't know. But there's a maximum number of rabbits. That maximum we're going to call L. And I drew this on the board last week. There's some maximum. Right? Then, if you look at the growth rate starts off exponential growth, and then it flattens. It flattens a little bit. Well, it doesn't flatten to 0, and then it starts slowing down a lot noticeably. All right. Here's the key. Here's the key sort of assumption. Oh, by the way, it can go this way too. Before I get going, it can also do this. There's logistic decay as well, right? Logistic decay. Now, let's do a let's, the variable on the vertical axis is y. So that means this distance here, from there to there, is y. Right? And so that means this distance here is capital L minus y. Okay. We're going to need that. Now, hang tight a second. Every new individual is going to lower the growth rate by the same amount. Okay. By the same amount. And so if the whole system will support L rabbits, that means every rabbit that goes in will reduce the growth rate by 1 over L.
Is there a point where it stabilizes?
Yeah, actually, this is the upper threshold right here, an equilibrium. That's a very good question. And in real life, that's where a lot of times you're interested in. Where will the equilibrium occur? All right. Another thing is I think I mentioned to you at some point in the past about I grew up in Florida with alligators, and alligators were an endangered species when I was growing up because they were over harvested. They'd hunt them too much for their skin and their meat and everything. Okay? And just like buffalo out in this part of the country, buffalo went from the millions and millions down to just a few tens of thousands, and it took some intervention to bring them back. So when I grew up, you couldn't touch an alligator in Florida. They were endangered. Yeah, you would be severely punished. Problem was, after a while, with no predators, right? Alligators have not that many predators, you know. What happens? Well, they start appearing in people's swimming pool, right? And little Fifi the dog disappears. So there it is.
Now we're going to a restaurant again.
Yeah. You know what? I'll give you a little clue. If across the hall is empty, there's one of those restrooms across the hall at work. So when there's nobody in that room, that's a good time to go to the restroom. All right. Not a good time if there's a class there. Right? Because I used to teach class in here when that restroom worked. That's how long I've been working here. I remember when the restrooms worked. And that was a restroom right there. And you'd be in class and somebody would go back there. The problem is that restroom, and so does that one, has all hard surfaces. Tile floors, all hard surfaces. It's an echo chamber. So all the bathroom sounds get okay, like reverberated. And so I'd be up here in class. Sometimes I'd have 30 in this classroom, and somebody get up and go to the bathroom back there, and you hear all these sounds, right? And people I hear are going. The person comes out, and everybody's dying. You're killing me, Smalls. Right? So back to this. So every individual that enters the population lowers it by 1 over L. L is the limit. L is the limit. Okay. So what does that look like? So instead of this was your growth rate. Remember, this was your growth rate. Now, what's your growth rate going to be? You're going to lower that by 1 over L for every increased individual, right? And so, if you subtract 1 over L times whatever the population is. that, right? If you subtract that, you can then factor I'm not quite pleased with my now what I just said. Let me see here. Actually, let's get rid of that. Let's just do, sorry, let's just do this down here. My apologies. Right here. Here's your KY. This looks a lot like that. Right? That part's the same. Right? Except this is KY times 1. This is KY times 1 reduced by this. And this Y can't get bigger than L, right? Y cannot be bigger than L. So this is always going to be positive. Now, it turns out it does work in real life. It does work the other way. Suppose you had an ecosystem. Suppose you had a lake, and the lake will support 2,000 fish. And somebody puts 2,500 fish in there, 500 extra fish. So if you put in something up here, this model will bring it down to there. It will always want to return to L. Right? So this is what our logistic differential equation looks like. And now we have to solve it. We're going to solve this for Y. All right? That's very important. We're going to solve that for Y. Now, it turns out we're going to need a procedure called partial fraction. You know what? The slides I was just looking at in chapter 8 was partial fractions. Partial fractions has 4 cases that we're going to study. This is the simplest case, case 1. Okay? I'm putting it in here for your reference. It's in the book. I'm not going to go over it. I'm going to go over it when we encounter it in the problem. But here is the same equation, right, as before on the other slide. Solve it. What are we going to do? Here. What are we going to do? Well, right now, what do we have? We have separable and first order. I'm sorry. We have separable and we have homogeneous differential equations. Those are our 2 types, right? And you go, okay. I have to get this separable. Yeah. How do I do that? Either separable or a point, if I can't separate it, a point that is homogeneous. So what we're going to do is we're going to combine these 2 things in here. This 1 is L over L, right? That 1 is L over L. So capital L minus Y divided by L. And that is dy dt. Oh, there's no X here, right? All right. So dy is going to equal let's break this up. Y times L minus Y divided by L times that K dt. And that gives you, actually, I'm going to move this over to the left. I'm going to have to move this to the left. That gives you what? We're going to have to solve, we have to put the y's on the other side, right? The y's got to go on the other side. These y's, that y right there, those y's got to go over here. And so this equals, multiply by the inverse. And so you see that it is separable. The cool part is you didn't even have to do the y equals vx thing, right? You didn't have to do the y equals vx. So it was separable without, it wasn't, you didn't have to do the homogeneous part, right? Question. Got to integrate both sides. So now I'm going to go integral, integral. Sorry. All right. Pop quiz. Jesus is on. Licon. Get that closer? Licon. Okay. Fisher. Equality here, okay? The easy names are hard names. Well, hard for, I'm trying to. When I was in grad school, the majority of my classmates when I was in economics graduate school were Asian of some kind. And the majority of them were Chinese or from Taiwan. Both are Chinese, but Chinese nationals, from mainland, or from Taiwan or Hong Kong. And they all took names like Pete and Larry, and I mean, just ordinary Anglo-Saxon names, right? I said, no, I want to learn your real name. It was really, really hard. Oh, I had some Koreans. I learned every one of them, 50-something people in the program. I learned all of them their real name. And I appreciate what they were doing. They were using Anglo-Saxon names to make it easier on us. But I wanted to learn about their culture. It was kind of cool to do that. So what do we do here? Pop quiz over here. The integral of 1 dt is t. So the right-hand side.
That was easy.
That was smart. This side, I would let you struggle with it, but guess what? We haven't learned that yet. I'm going to come clean. That's why I include the previous slide. For this one here, we need integration by partial fractions. There's no way to make the top the derivative of the bottom. What's the derivative of the bottom? I'm going to erase what I'm going to do. What's the derivative of the bottom? YL minus y squared. So the derivative would be L minus 2y. How can you make that top the derivative of the bottom? I could put minus 2y there. I could subtract 2y, but then I'd have to add 2y somewhere. And that turns out a bigger mess. So what do? I can't make the top conveniently into the derivative of the bottom. And so the technique is what is on the previous page. It's called partial fractions. So we're going to go over here and we're going to do partial fractions is an algebra technique. There's no calculus in partial fractions. Just partial fractions helps us with calculus. It helps us. So what do we have? We're going to have this. It turns out we're going to break this up and we're going to write it as 2 fractions. And so the technique is, and you're not responding. This is something you're not expected to have known right now. We're going to do it, and you're going to do it in chapter 8 anyway, right? So I won't give you one on the test that uses this in chapter 6, but we'll show it to you. So you got L over y, L minus y. The variable is y. L is a constant. So the method of partial fractions says this can be written as A over the first factor in the denominator plus b divided by the second factor in the denominator. Okay. Okay. Now, this is a theorem we're doing. We're using a theorem that says this is possible. All right. Now, how do we go about finding A? If we find A and B, we're done. So we put over here, must find A and B. Right. Did I mention this is chapter 8? You're going to learn this anyway. So let's add the right-hand side. If I just added it using ordinary properties of fractions, what would my denominator be? It's going to be this denominator here. On the first term, I got to multiply top and bottom by L minus Y. So I'm going to have A times L minus Y, top and bottom here, right? Here, I need a Y in top and bottom. So plus B times Y. And if it makes you feel better, like right here, you can put L minus Y there and L minus Y there. And you can put times Y here, times Y there. You can put in a preliminary step. You see here, I'm multiplying top and bottom by the same thing. That's multiplying by 1. Here, I'm multiplying top and bottom by the same thing, which is multiplying by 1. That gave me the common denominator, and the top becomes what I have here.
It's like cross multiply technically.
We didn't cross multiply there. We didn't cross multiply there. We just added fractions. So if I have, I'm going to erase this. But if I have A over B plus C over D, to add those, I need to do A over B. My denominator is going to be BD. So I have to multiply by D over D. Oh. What a bad time that time. We have a crash. Let's see how much we lose. You know what I'm going to do first? I'm going to do this. I'm going to take a screenshot. But the short answer is it is not. It is not. Here, I need that. All right. So now I'm going to go here. Back here. We have 5 more minutes of class, and we're going to finish this example. Now that I crashed in that spot.
It feels like a Monday.
It feels like a Monday. It's a Monday Tuesday. It's a Monday Tuesday. You're absolutely right, bro. It is a Monday Tuesday. I had a good weekend too. So
What you do?
well, got stuff done on Saturday, which was very, very satisfying. And then Saturday afternoon and evening, a bunch of us got together in a big building in York, and we had a bunch of church Christians got together, had a dinner together, and we had a time of singing and praise. That was fun with my bunch of 40 or 50 friends. And then Sunday was mainly church. And then I have a small group that meets in my house. from the church. So that's the evening. It goes into the wee hours. And we had some friends staying with us also for the weekend. That's a whole other thing. They've been staying for a while. And then on Monday, yesterday, I went to actually a preacher's workshop, like a meeting of Nebraska Church of Christ preachers. I am not a preacher, but I'm an elder at the East Hill Church, and so I went with our minister to attend this thing, just to spend time with those people out there. Because I know most of the Nebraska Church of Christ preachers, and so that was really good. So I was kind of like coming. Oh, look what we got here. Oh no,
You don't watch football?
I did not watch any football.
They're good games.
Was it a good game? I used to watch football. I used to. Okay, let's try this again real quick before we can go. Let's see here. This is D divided by D. You multiply that by 1. D over D is 1. Then you're going to multiply the second one by B over B. Right? So there's no cross multiplying going on. This is going to be AD plus BC divided by BD. That's just basic fractions. Okay? No cross multiplying going on. All right, so here we now have the numerators are equal. These denominators are equal, so the numerators must be, right? I'll just write this here for fun. So these two are equal, so those two must be. So we're going to take those down here, and it's going to be L equals A L minus Y plus B Y. Okay, I'll just speed up a little bit here. What I need to do is solve for A and B. I need to solve for A and B. Now, I'm going to do one more step here. This is A L minus AY plus BY equals L. Now, I'm going to call this here the left-hand side. And this is the right-hand side, RHS. And so I'm going to have make a little chart here. And I'm going to collect how many Y's do I have? Left-hand side, right-hand side. How many Y's do I have on the left? 0. How many Y's do I have on the right? Minus A plus B, because this is minus A plus B all times Y, right? So it's minus A plus B. Then, how many constants do I have on the left? Constants on the left? L. How many constants on the right? A times L. Not AL. So this one, this implies that A minus A plus B equals 0, or A equals B. This implies that A just equals L. Wait a minute here. We got a problem. I have AL here, sorry. AL for constant. And so that means that AL equals L. Those cancel. And that means that A equals 1. But if A equals 1, A equals B, so B equals 1. And here's where we're going to stop. This means we have A and B. So our fraction, L, divided by Y, L minus Y, equals 1 over, what was my original one up here? 1 over Y plus 1 over L minus Y. So this thing right here equals that, and we know how to integrate both of those. Both those go to logs, right? So last thing here, bracket, we're going to have 1 over Y plus 1 over L minus Y dy equal to K integral dt, and we're going to leave it there. Right? Oh, we're a minute over. I'll give you that minute back. Oh, I'll let you out early at some point. Try to. 37, 32, yeah. Okay. That was some deeper waters. Well, you know, just the algebra and stuff. No real deep calculus, actually. It's just the procedure, right? So you got your plate pretty full this week with your getting the derivative that didn't get done last week. And then we have a derivative quiz on Friday for the new stuff. So just put that in your schedule in the next few days.
See you tomorrow.
See ya.